linear differential equation, okay, the response due to initial displacement x0 would be the half of the response of the initial displacement of 2x0. Right? If you have n times bigger initial displacement, then the response would be n times bigger the response than we had before, because that is linear. Okay, that's the concept of a linear system. What about this case? This is not linear case. Therefore, principle of superposition does not hold. So the argument to be used for this equation cannot be applied for nonlinear differential equation. In other words, the response cannot be twice, even if we have twice bigger initial condition for this case. Okay? So I am showing three different concepts. Modeling concept, get a differential equation, and then I introduced concept of linearity, principle of superposition. That's the key concept you have to understand. Okay, because this is a linear differential equation, the solution can be obtained by solving the equation okay, or because this is a linear differential equation with initial condition, we can use Laplace transform. Okay? Take Laplace transformation of this equation. Then we can get the solution in S domain. And then back transform it to time domain. Then we will have exactly the same solution as we show over here. Or lastly, what we can do? What would be the last method to get the solution? Direct integration. Meaning that I will integrate this equation with respect to time. Okay, for simplicity, let's think that I have only Cx dot and Kx. For simplicity. Let's start with x dot t equal axt. Right? If you know this, then probably we can understand how to solve or how to get the solution or the response of mx double dot cx dot plus kx equals 0 numerically. Okay? So let's see this case. And we know that this can be approximately written as plus 1. Meaning that I have time scale over here, and the system response start at time t equals 0. And then assuming that I want to calculate the response for time tf as used in the text. And then I divide this interval by n. Okay, and this time interval delta t would be tf over n. Okay, and this is xi, and this is xi plus 1. And the derivative with respect to time at xi would be approximate as the slope that connecting these two values. Okay, that is Euler's formula. So meaning that we are using Euler's formula to approximate the time rate of change of value of x with respect to time. Okay? Using this, what we can have is the xi plus 1, which I want to calculate, is the same as xi plus delta t a xi. Okay? Meaning that this formula essentially says that I can estimate the value xi plus 1, which is one step advance the value of present value, that is xi, by using this formula. Okay? This is a very crude but efficient way to estimate the value of xi plus 1 based on xi. Okay? This can be done numerically and using the MATLAB you learned the recitation. But this is crude, and as illustrated in the text, there's some error. It's not precisely correct. Of course, one may say, if I reduce delta t, very small value, meaning that if I increase n from 10 to 100, 1,000, 10,000, 100,000, of course the approximation getting better and better. And I'm not doing calculation 10,000 times because computer is doing all the business, and I can increase delta t and not 10,000 times but maybe 10 million. Then one may say I will have exactly correct solution that I expect. Is it correct? No, because computer always has his own source of error. Okay, that we called round-off error. So there is a round-off error that is inherently present